Right. Hello everyone. Can everyone hear me? So if there's any issues with the audio or the stream is lagging too much, just please let me know. Okay, so I will just take it as it should be fine. So just like the SMO, this session is going to be 2.5 hours long. So feel free to move around, especially if you took the SMO Open this morning. I think you've had quite a bit of math today. So try to relax, don't get too stressed, and have a snack, a drink in front of you and move around if you have to. Now this session is not for everybody to get exactly the questions they want to know. It is meant to go through everything. So I think for a few of you, you might have done 20 over questions. If that's the case, I'm still going to go through everything. So if you want to step aside and then just come back for those questions you think you want to know more about, that's fine, because this is aimed at a general audience. Now for now we haven't started, so it's fine. But when we do get to the discussion later, just a few guidelines for the chat. So one, just let me know if you have any visual and audio issues. Two, if I make any serious mistake, mathematical mistake along the way, let me know. It can certainly happen over a 2.5 hour session that I say something really silly. So please tell me if I do. And along the way, if there's any questions you have, do type it into the chat. Now, if there's a few of you who ask the same thing, most likely I'll address it. If it's one or two of you, I'll see how the time is like. As I said, I won't be able to attend to every single question. And if you have a better method, please let me know, because I did not get any prior access to these questions. So I've been preparing for both the junior, senior, and open sessions pretty much right at the same time as you, just maybe a few hours after. Now, please don't spam the chat, especially during our solution discussion later. Don't use offensive language, and don't go and fill up the chat with how much do I need to get a bronze, how much do I need to get a silver, how much do I need to get a gold, what is the cutoff for the top 10. I don't know, and I certainly wouldn't want to hazard a guess. The most I'm going to say for now is that it certainly is a bit more difficult than the previous few years. And I would presume that's because there's a need to select the junior, senior, and national team only using the first round. So there are a few more difficult questions than usual, but I won't be able to tell you, what is the gold cutoff or silver cutoff. So please don't engage in too much of these discussions, except during the break times. That's probably okay. But during the break times, do also try to be polite and tactful when discussing. Don't go say everything's trivial and say that, I saw 24 questions, only one question is difficult, the rest are super easy. Please be mindful of one another. There are some of you who have done Olympiads for a long time, and there are some of you who have just started and have less experience. Now, my plan is not to go through every single nitty-gritty detail. I'm going to just mention the motivation, a few key pointers for every question, and any theorem that is not universally known, I will mention in more detail. So for example, the quadratic formula I'm not going to explain, the binomial theorem I'm not going to explain, but if let's say I use Cauchy-Schwarz, I will explain. So I think that is a reasonable balance, but this is not a lesson. So I'm also not going to leave you lots of time to copy down notes. Just pick up the ideas, and if you need to, you can always look back at the video if you want to note down a couple of identities, formulas, or solutions. It's something that your math teachers always say, but it's probably important to mention, right? It's not just about the final answers for the SMO, and it certainly isn't about how you did. If you got halfway through a question and you missed one key insight, that's also laudable. It's not going to give you an extra mark in the SMO, unfortunately, but that is still worth recognizing. So please don't get too hung up on, I didn't get this question, so I listened. The other questions, I don't listen. It's okay if you got it right and you want to just walk off for a while, but don't entirely shut your brain out. Maybe there is a faster method or even a totally different method which you didn't consider. And conversely, if you failed to solve a question, the reason why we're doing this so close to the SMO is because you will remember why you got stuck. You will definitely remember which question frustrated you the most and made you really angry. And when I go through the problems, think about why you didn't find the solution. Was there anything that you missed out or you forgot? And hopefully from there you'll pick up a bit more. So a little bit about me. Not all of you will know me personally. So my name is Wei and I was from NUS High and I just graduated from NUS not too long ago. Now I understand that perhaps some of my teachers are joining in this session. If so, welcome and hello. And this is a very incomplete story of my educational history, but I'm not going to get into that here. You will know what I mean. I have taken the SMO like all of you here, presumably, and I have done well. And my interest in math doesn't just stop at math Olympiads. It goes pretty far beyond that to in my university studies, to doing research, or just to solving puzzles and all kinds of math related things. But at the same time, I was in the national team for a few years and I didn't make the IMO team. There's no shame in that, but the reason why I'm mentioning this, and I did this yesterday as well, is that there is something that taught me and I learned in retrospect, which is that I always was doing quite well in the SMO, and so I was pretty happy with what I scored. But then I may not actually have even found out how to solve those questions that I didn't do. When I did the practice on my own, it was always about doing more questions, and that's great. But for those few problems that you didn't solve, it's just as important to know what's the solution because that's where the most of the learning is. So the reason for this session also is that if there are some of you who solved 22 questions, then use this to learn the other 3 questions. Maybe there's some theorem you didn't know, or maybe there was a type of manipulation which you didn't think of. Now, a couple of acknowledgements before I start, and part of the reason for this is just to let people come in. So this is not an official SMS affiliated event. The logo is there because that is the logo of the Math Society who organized the SMO. Right? But my solutions here are not official solutions, meaning that I'm quite sure they're correct, but they may not be the one that was intended by the problem setter. So if you were to see a solution that you think is quite convoluted, that may not be the best solution. That's just the best that I could come up with. So feel free to suggest any alternatives in the chat. You'll see the logo of Maths Hub as well. That's where I'm currently teaching. So my thanks to for their support in giving me a physical location and a little bit of publicity and technical resources. But this is also not an official activity for the center. So this is something that I'm doing on an independent basis. Okay, and thanks to Lim Lee and family for helping to publicize this session on their blog, where I think a lot of you have gone to see the answers already. I also understand an email has just gone out in NUS High a while ago, so thanks to Mr. Wang and Dr. Lee Chan Lai for also helping me to disseminate the info. Right? I'm a very, very invisible alumni, but I am still NUS High alumni after all. Alright, so without further ado, I will get into the SMO senior questions, and I will take a couple of breaks in between, maybe after the first 10 questions or so. So at that point, if you want to discuss about cutoffs and marks and ask about how things are going for your friends or for whoever it is, that would be the time. But for now, let's keep to the questions proper. Now, I think the MCQ questions as a whole are not too bad, so I'll try to move through them a bit more quickly. For question 1, let P be a real number such that the equation x squared minus 10x equals to P has no real solution. This is a fairly soft start because is just a quadratic equation, and your quadratic equation with no real solution means that the discriminant is negative. Okay, so discriminant is negative, and this is a very direct problem. So if you solve the equation, P is less than negative 25, and you have your first mark of the SMO senior. Yeah, unfortunately, the rest of them don't come that easy. So in the SMO Junior, there was a similar question this year. We can use completing the square in that context. So here you can use completing the square too, but at the senior level, I will choose to use the discriminant. For question 2, which of the following is the largest? And you notice that all of these have to do with sine, cosine, and tangent of 50 degrees. So you need to have an idea of 50 degrees. So let's draw a triangle. A right-angled triangle, and let's say this is 50 degrees. And the hypotenuse is 1. So as we know, this would be sine 50 degrees and cosine 50 degrees. So this is a pictorial depiction of why sine 50 degrees is larger than cosine 50 degrees. Now you could also have used the unit circle, or you could have used the graph to deduce this. Either way, since sine is larger than cosine, that means that the tangent is bigger than 1, because tangent is sine divided by cosine. So that means that if we were to look at these options here, I can kind of put every of the expressions in order, that tangent is more than sine and cosine because it's greater than 1. So in order of in descending order, you will first have tangent, then you have 1, and then you have sine, and then you have cosine. Now comparing all of these, it is quite clear that tangent plus sine would be the largest. And take note that sine squared and cosine squared would both be less than sine and cosine themselves, because you are squaring something that is less than 1. Okay, so that means that the ones with sine squared and cosine squared are even worse. Let's just put that down for completeness sake. So A is the largest, and we can move on to question 3. Find the value of 2021 to the power of log 2021 2020, log 2020 2019, log 2019 2018. Now I think there are many different ways you can look at logarithms, and one way you can look at logarithms is that every logarithm is actually a ratio of logarithms. And what I'm saying here is your change of base formula. So what you have in the exponent can be easily simplified using the change of base formula into a bunch of fractions with the same base of logarithms. You can write it as log 2020 over log 2021, log 2019 over log 2020, and the base is not very important, so when the base is not very important, I can just use log in the usual way, which is log base 10, since it's going to be gotten rid of pretty soon. Now notice that these will all cancel out. So you're left with log 2018 over log 2021, which you can combine back again into log 2021, 2018. Therefore, your answer is 2021 to the power of this, which is 2018. Question 4. Suppose that sine theta equals to n minus 3 over n plus 5 and cosine theta equals to 4 minus 2n over n plus 5 for some integer n. Find the maximum value of 160 tangent squared theta. Now when I see this, one of my instincts is that should I find out when sine theta and cosine theta are between minus 1 and 1? And I think that would also narrow down n quite a lot. However, the one that restricts it immediately rather than giving you a range is sine squared plus cosine squared equals to 1. Think of sine and cosine as really closely related sibling functions. They pop up all over the place. Sine squared plus cosine squared is 1. Sine theta is cosine of 90 degrees minus theta, and that's actually where the name cosine comes from. Cosine is sine of the complementary angle. Furthermore, as some of you know from calculus, if you differentiate sine, you get cosine, and if you differentiate cosine, you get negative sine. So there are lots of ways in which they are related. But we picked this one because it's the most ideal to tell you what is n. So n minus 3 squared plus 4 minus 2n squared over n plus 5 squared should be equal to 1. Now multiply over and expand everything. You should get 5n squared minus 6 and minus 16, so minus 22n, plus 9 plus 16, so plus 25, and multiply over, you get n squared plus 10n plus 25. Move everything to the left. 4n squared minus 32n equals to 0, and so n equals to 0 or 8. Now n equals to 0 and 8 are therefore your two possibilities, and if you substitute them in for n equals to 0, so we just want to check that it really falls into the range of minus 1 to 1. Right? That's the main reason why we're doing this, and to make sure that it is not giving you anything undefined, which would clearly not happen, just in case. So sine theta would be minus 3/5. Cosine theta would be 4/5. For the other case, sine theta would be 5 over 13, while cosine theta would be minus 12 over 13. The moment I see this, I can kind of tell that the SMO problem setter was trying to reverse engineer this from 5, 12, 13 and 3, 4, 5. So that's why you get these rather odd looking fractions over here. He wanted to make sure that for two particular values of n, these two ratios, 3, 4, 5 and 5, 12, 13 will show up. Anyway, this first case, since tangent is sine over cosine, the first case gives you tangent theta is minus 3/4. And the other case gives you tangent theta is minus 5 over 12. And since you want the larger one, you pick tangent theta equals to minus 3/4. Now substituting that in, your answer would be 90. Okay, finally question 5. Select all the inequalities which hold for all real values of x and y. This question would be a little bit more difficult if it wasn't in the MCQ section, or if they asked you how many of them. Because here, if you just check the correct ones, you would already get the intended conclusion. Now, among all of these 5 inequalities, 3 of them can actually be rearranged to look something like the equation of a circle. So you can look at those to check whether it will work out like the equation of a circle, because it will hopefully give you something squared plus something squared is greater than or equals to 0. If that happens, then those are valid. If not, then it's invalid. So for I, if you rearrange it on the right hand side, you get x squared minus x plus y squared. And you can complete the square here. Oops. Complete the square. And so you know that this is not true because you can let x equals to half and y equals to 0. So therefore this is false. Likewise, you can do the same for part 3. And complete the square for both of them. And once again, you know that if you substitute in half and negative half, this inequality is not true. Finally, for part 5, if you move everything over, and you complete the square, you will get the sum of 2 squares plus half, which is certainly greater than or equal to 0. So therefore this is true. Now technically at this point, since you already know that 1 and 3 are wrong and 5 is correct, you already know that the correct answer is E, right? But for completeness sake, let's just look at 2 and 4. Now for 2, we know that x squared plus y squared is greater than or equals to 2xy. That's for by either AMGM or just by moving it to the left and completing the square. Now if xy is both positive, x times y I mean is positive, then 2xy would be in turn larger than xy, so the inequality is true. Now if xy is less than 0, then x squared plus y squared is already more than 0, so it will still be true. In other words, option 2 is always true regardless. Now finally for option 4, option 4 is false because, and I'll just give a counter example, even though we can also complete the square. So my counter example would be when x is 0 and y is, let's say, 1/2. Some of you may correctly point out that, hey, I could have done counter examples for 1 and 3 as well. Why should I have done something like complete the square so many times? If you say that, my answer is you are right. We did not have to complete the square so many times, but I wanted to contrast 1 and 3 versus 5 in terms of why is it that 5 is true whereas 1 and 3 are not true, even though they look somewhat related to one another. Okay, so that brings us to the end of the MCQ section, and I think we can move on to a few more questions before we have a short break. Question 6. Let x be the integer such that x equals to 5 to the power of the square root of 2 plus 4 log base x of 5. The moment you see x and 5, and then you see x and 5 again, things that appear more than once in the same equation are usually not there by sheer coincidence. So how do we continue? We take log base 5 of both sides. Okay. And then I will square both sides of this to get rid of the square root. And take note that log base x of 5 is the reciprocal of log base 5 of x. So since they're all related, I'm going to just let a be log base 5 of x so that we can replace all this just by a variable a. So a squared equals to 2 plus 4 over a. Now since x is an integer, you know that x cannot be negative, otherwise it's undefined. So x is positive, and if x is positive, a would be greater than or equal to 0. So if a is greater than or equal to 0, and we look at this on this equation over here, we could go and move the a over and try to factorize the cubic. However, a quick observation is that a squared is increasing, while 2 plus 4 over a is decreasing as we move a. In other words, there should only be one solution, and all we need to do is guess that solution since there's only one. So the only solution is a equals to 2, which is not very difficult to see actually, because a squared is going to get much bigger than this in no time. So you try 1, and then you try 2, and that's it. So since this is the only solution, then x is 5 to the power of a is 25. Question 7 is a bit misplaced in my opinion, because I didn't see a super quick solution for this. So it's a bit more difficult than you would expect question 7 to be in based on recent times. Okay, so we are told that cosine A minus cosine B is half, and sine A minus sine B is negative 1/4, and we're asked to find the value of 100 sine A plus B. Now I did notice that for some reason the question setter seemed pretty fond of something like this year, because the SMO Open just today had about 2 questions that look rather similar to this as well. So how do we proceed here? Now actually there are a host of reasonable things to do, and I'm going to acknowledge all of them, because if you do some combination of these things, you should be fine. Now what could you do? You could square the equations and add. You could square the equations and subtract. You could also have tried to add or subtract the equations immediately. You could also have tried to multiply the equations. You could have tried a geometric interpretation and drawn a triangle. Now the reason why I write all this down is because I considered all of this, and quite a number of these give something useful. Meaning that there are many solutions passed for this question, but none of them just involve one step. So you need to combine more than one thing, but which exactly that is really up to you. So what I'm going to show is just one possible method out of many. Okay. And my approach is going to be by the sum to product identities, or the factor formulas as some of you may otherwise call it. So using sum to product, why do I want to use sum to product? Because I can see that a plus b over 2 is going to show up. even before doing the details. Okay. So for the first one, this is from your sum to product, and so therefore sine a plus b over 2, sine a minus b over 2 is negative 1/4. If we use the sum to product on the other one, it gives you 2 cosine a plus b over 2 sine a minus b over 2 equals to minus 1/4. I'll divide by 2 over, and it tells you that cosine a plus b over 2 sine a minus b over 2 equals to negative 1/8. So these are my two equations now, and we're actually closer than we think, just after applying these factor formulas. I'm going to just number these two equations 1 and 2 for convenience. Firstly, if you want to make sine a plus b appear, I can multiply the two equations together, because that would give me 2 sine a plus b over 2 cosine a plus b over 2 roughly being somewhere there. Okay, so the first thing I do is multiply the equations. If I multiply the two equations, sine times cosine is 1/2 of the double angle formula, which is a sine a plus b. If you multiply the other two, is sine squared a minus b over 2. And this is equal to 1 over 32. Now, in turn, how do I get sine a minus b over 2? I can square the equations and add them, because sine squared plus cosine squared is 1. So that's the other step that I will do with these two equations. Now, by doing that, the front sine squared plus cosine squared is a factor that disappears. So you get sine squared a minus b over 2 is equal to 1 over 16 plus 1 over 64. So this is great, because we can now just substitute it in. And solving, you will get sine a plus b is 4/5. And your answer is 80. So if anyone has an even shorter method, do feel free to type it into the chat or to write it in the comments later. But I think this is the cleanest approach that I could think of for such a problem. If anyone took the SMO Open this morning, hey, this might actually be useful for the question with sine A plus sine B and cosine A plus cosine B, and asking you to get tangent A plus tangent B. You could have used the first equation divided by the second equation and done something similar as well. We'll talk about those questions tomorrow anyway in the live stream for the SMO Open. So if you took the Open this morning and you're curious about that more than this paper, feel free to pop in tomorrow as well. Question 8. Find the constant in the expansion of, this looks painful, the cube root of x plus 1 over square root x to the power of 6 times square root x plus 1 over x to the power of 10. Now this kind of subverts what we expect, because we have seen quite a lot of these kinds of problems with only polynomials inside. In other words, finding just integer exponents versus something that looks a bit messy. However, this is not so bad if we try to make things a bit easier for ourselves. So what I'll do is that I will factorize it. I'll take out 1 over square root x to the power of 6. And then the remaining part, x to the 1/3 plus x to the 1/2, will be x to the 5/6 plus 1. Square root x plus 1 over x to the power of 10. I'll factorize out 1 over x to the power of 10. And that leaves me with x to the power of 3/2 plus 1, then to the power of 10. So the product of these two, 1 over root x to the power of 6 and 1 over x to the power of 10, you get x to the power of negative 13 in front of this. Okay. You want to look for a couple of terms in these two brackets that will nicely cancel off your x to the power of negative 13. So let's suppose that you're looking for that term. What you're looking for is some power of x to the 5/6 and some power of x to the 3/2 that is exactly 13. In other words, let's write the general terms down. You have, let's say, 6 truths a times x to the 5/6a, and then you have 10 truths b to the power times x to the power of 3/2 b. And what you want is for this to nicely cancel out the front. So 5 over 6a plus 3 over 2b is equal to 13. Where of course a is between 0 and 6 and b is between 0 and 10. Now multiply everything by 6, you get 5a plus 9b equals to 78. And since a is between 0 and 6, it should be not very difficult to just check a couple of cases, and you will find that a is equal to 3, b is equal to 7, and that's the only term that you can use to give you a constant. Therefore, your answer becomes from here and here, 6 truths 3 multiplied by 10 truths 7. So this is equal to 20 times 120, which is 2400. Now you could have used the general term at the start, that's also fine. I just thought that this was a bit nicer looking. If you use the general term at the very start and you got 1/3 a minus half 6 minus a and so on, you would get something almost equivalent to this. But it's just a personal preference where if you make one of them into 1, makes it a bit easier to work with for the rest of the question. Okay, question 9. A quadratic polynomial px equals to ax squared plus bx plus c, where a is non-zero, has the property that pn equals to 1 over n squared for n equals to -1, 2, and 3. Find the smallest possible positive value of k apart from 2 and 3 such that p of k equals to 1 over k squared. So this is quite interesting. So they are giving you a quadratic. The quadratic behaves like this for 3 values, and they're asking you what's the other positive value where this also works out. Now, if you have encountered such problems before, you would know that it is related to the factor theorem. How you write it is that px equals to 1 over x squared for x equals to -1, 2, and 3. So if we multiply over x squared and subtract 1, then x squared px minus 1 equals to 0 for x equals to -1, 2, and 3. Perhaps in a slight twist from our usual expectations, this does not immediately tell us our answer because x squared px minus 1 is a quartic. Quartic means degree 4. And there are 3 roots that are given to you. So that means that you have a quartic with 3 known roots. There's still one more root that we don't know, and that's actually the thing that you're supposed to find. That is the other k that you're looking for. Okay, so let's write it like this. That means that x squared px minus 1, oops, brackets in the wrong place. We know 3 of the factors, x plus 1, x minus 2, x minus 3. There's one more factor that we don't know, which is x minus k. Let's write it. And there's still a constant, which is, let's not use a, b, and c. Although actually if we compare the coefficients, we can just call it a. Because the x to the power of 4 term on the left hand side is ax to the power of 4. So the constant here should be a. Now we need to find out what is k using this equation over here. So my suggestion, whenever anyone encounters this, is first, is there any value you can substitute such that you don't need to know what is the value of px? The answer to that question is yes, you can substitute x equals to 0. Because if you let x equals to 0, you don't need to know what is p0. So -1 equals to a times 1 minus 2 minus 3 minus k. So ak equals to 1/6. So that's one equation. Now to find the other equation, you need to compare something else on the left side and right side. And there's no other value that we can substitute in anymore without having to know what is p of x. However, we know that on the left hand side, because we multiplied by x squared, the x coefficient is 0. So this is really convenient. It means that we can compare a second coefficient, and that will give us another equation for a and k. So we compare the x coefficient. Now to be fair, comparing the constant coefficient is the same as x equals to 0, so if you put it that way, that's also fine. But we'll compare the x coefficient. Now 0 equals to a times, and this is a little bit annoying, but let's just work through it. The coefficient of x is 1 times -2 times -3, which is 6. 1 times -2 times -k, which is 2k. 1 times -3 times -k, that's 3k. And then -2 times -3 times -k, which is -6k. And if we simplify, this gives you 0 equals to a times 6 minus k. Hey, that actually gives you the answer because a cannot be 0. So therefore k equals to 6. And in fact, the thing on top wasn't really important unless we also wanted to know what is the value of a. Now, some of you would have just done this in the direct approach. You substituted in -1, 2, and 3, and then solved the simultaneous equations for A, B, and C. And then after that, you took that quadratic equation, and then you tried to find the other value where this is true. That's possible, but quite a bit more messy. Now, some of you are then saying that actually we can use Vietas for this. And the answer is that yes, this could be equivalent to Vietas, because this would be basically the x coefficient is the pairwise sum, so it's the sum of the products of 3 roots at a time. So I'll just put a remark here that this is equivalent to Vietas, but I'm not assuming that everyone knows Vietas for quartic equations. Okay. So I'm just sticking to a more traditional approach over here. Now finally, for this section, I think we'll look at question 10 and then we'll stop for a few minute break. So in question 10, we have a triangle ABC. AD and BE are altitudes, and then they intersect at a point H. As many of you may know, this point H is the orthocenter, and there are a bunch of properties about the orthocenter which could be really useful to solve this question quite fast. However, you don't actually need to know the properties of the orthocenter to solve this. Similar triangles would more than suffice. They tell us a couple of lengths, 50 and 18. And they also tell you that BH equals to EH. So what we're supposed to find is the area of the triangle, which essentially means that if you know AD, you want to find BC or something else related to that. So let's see how this can be done. Now, the first thing that would immediately stand out to me is that there are a couple of similar triangles, AEH and BDH. Now, these two triangles are similar to one another, and so therefore these two equal lengths, if we call it x, we can find them fairly immediately. It tells you that 50 over x equals to x over 18. So if you cross multiply and solve, x equals to 30. Now, a couple of you may have seen this in a different way. You may have seen that actually A, B, D, E are concyclic because of AEB and ADB being right angles. So since this is cyclic, we can use power of a point or the intersecting chords theorem to say that AH times HD equals to BH times HE. That will reduce the same equation, because remember that power of a point or your intersecting chords, intersecting sequence theorems all come from similar triangles as well. So really, we are doing the same thing if that's what you are thinking in your mind. Okay, so that means that x is 30, and we want to find some more lengths. Now notice that a lot of angles in this figure are actually all equal to one another. So this same angle specifically appears 2 times, and we already see that this is 30 and 50, so your AEH is a 3, 4, 5 triangle, since there's a 30 and a 50. And that means that so is BDH, and so would ADC, because it also shares the angle. And so would BEC. So technically from here, there are lots of different 3, 4, 5 ratios you have, and you can take your pick of which one you want to use. Right? However, since already BE is 60, I think it's easier if we just get straight to triangle BEC. So in triangle BEC, BE over BC is 4:5. And BE is 60, so therefore BC is 75. And BC is 75, then we are basically there. So your area is half times 75 times 68. Please multiply it correctly at the end. You get 2550 as the area. Okay, so we have reached question 10, and I think we can maybe take a 5-minute break before carrying on for the next 8 or 9 questions. Okay, everyone, welcome back. Before we resume, I guess I've been reminded that I can do a little bit of shameless self-promotion. So if you have found this useful and interesting, and if you think that this is useful, please do like this video and subscribe to this channel. I think that's something that everyone on YouTube always says. Yeah, and obviously I do intend to put up more stuff subsequently that hopefully will be helpful for everyone. And that includes the SMO Open session tomorrow, which to be honest, I haven't actually looked at all the problems yet. So that will be what I'm busy with tonight after this session and after my other lessons are over. Right, so do join in. It looks like an interesting and challenging paper, but I think it will be a pretty useful discussion session to have. Okay, question 11 now. In the figure below, you have some right angles, which I shall mark out. GCB, ACE, which kind of seems a bit redundant, and DFE. And then you have got some angles that are theta. GBC is theta, EAC is also theta, and EDF is also theta. Furthermore, they tell you some lengths. GB is 6, AE is 10, and DE is 8, and S is the sum of the areas of triangles ABC and CDE. Okay, let's mark it out. ABC and CDE. So those are the two triangles that we need. Now we actually realize that there's nothing stopping us from really just finding out the areas of the triangles, except that it will be in terms of theta. So let's find it in terms of theta. First, ABC. Now to find the area of ABC, BC would be 6 cosine theta, while AC would be 10 cosine theta. Now, I presume from the 6, 8 or 10 appearing, you will know which triangle I'm referring to, so I'm not going to elaborate too much on where exactly it appears from. Now as for CDE, you need two things. Firstly, CE is 10 sine theta, and secondly, DF is 8 cosine theta. Now you realize that this is not really to scale, by the way, because the thetas should give you 3 similar right-angled triangles, but that certainly does not look very similar, especially if you look at GBC and CAE. So one of them is much less than 45, one of them is more than 45. So this is not really something where you want to use the diagram. You just use trigonometry directly. So the areas of these, half base times height, 30 cosine squared theta, and here 40 sine theta cosine theta. Generally for me, whenever I see any so-called degree 2 trigonometric expression, so degree 2 means that sine squared or sine times cosine or cosine squared, I immediately want to push it up to a double angle. And when you see maximum, you kind of have an inkling that it's the R formula involved. So let's push it up to a double angle and the R formula will do the rest of the work. So I'll sum 30 cosine squared theta plus 40 sine theta cos theta I can shift this over to cosine 2 theta. From cos 2 theta is 2 cosine squared minus 1. So this is 15 times of cos 2 theta plus 1. While this second one is 20 times of the sine double angle formula. So we have got 15 cosine 2 theta and 20 sine 2 theta, which we can then apply the R formula on, but the R formula only to get us the maximum value. So no need to deal with the gnarly tangent inverse of 4/3 or something like that. Okay, so this portion is less than or equal to square root of 15 squared plus 10 squared, which if you recognize is in the ratio 3:4, then you know that it's 345. This is 25, and 25 plus 15 means that your maximum is 40. Okay, question 12. Find the sum of all the solutions to the equation cube root x minus 110 minus cube root of x minus 381 is equal to 1. There was a rather similar looking question in the SMO Junior as well. That was at question 25, and yet fifth roots, I should say. That was something that we needed to do a bit of casework on. However, here there is no guarantee of it being integers in the place of x, and furthermore we only have cube roots. So since we only have cube roots, actually it's okay if we were to just solve it directly without using any number theoretic ideas or any bounding arguments. So here's what I'm going to do. I'm going to just call this whole thing A and this whole thing B. Now obviously, A minus B equals to 1 is my equation. And I want to make use of the fact that I can get rid of the cube roots without actually cubing the whole equation. So we write it like this. A cubed minus B cubed is the difference between the two on the inside, which is equals to 271, I should say. Now we hope to use these two over here and here to find out what is A and B, or at least to get enough information about A and B. Now you should know that A cubed minus B cubed, you can factorize out A minus B. And what's left is A squared plus AB plus B squared. So since this is 271 and this is 1, that means this is also 271. Now I can use that further to do one more step. I can take A minus B equals to 1 and square that. That's 1. And this is 271. So take the difference of these two, and that would give you something even nicer. So you take this, and you take this, you take the difference. 3AB is 270, so AB is 90. That means we now have two equations which are actually going to be just quadratic if you combine them. So if you take A minus B equals to 1 and you take AB equals to 90, you can substitute in A equals to B plus 1 into the second equation, and you solve it, and you actually get two very unsurprising solutions. AB can either be 10 and 9, or it can be minus 9 and minus 10. Neither should come as a very big surprise. The first because 90 is 10 times 9, and the second because they asked you for the sum of solutions, so having two of them kind of seems expected. So let's just wrap it up. That means that if a is 10 or minus 9, so x minus 110 can either be 10 cubed or negative 9 cubed. The first one is 1110. The second one is 110 minus 729, which is negative 619. And the sum of these two would be 491. Once again, this is not the only way to do it, but I think working with A's and B's kind of takes away the psychological barrier and the mistake proneness of dealing with the cube roots directly. Yep, this is 491 and not 441, the difference between 1110 and 619. Okay, next up, question 13. If fx is equal to 2x plus 4 plus x minus 2 over x plus 3 whole thing squared, where minus 2 is less than or equals to x less than or equals to 2, find the maximum value of fx. Some of you who have been very seasoned with these kinds of equations may be looking for AMGM in here. My answer to that is be careful when you want to use AMGM, because AMGM assumes that everything is positive. I've made that mistake before on a couple of occasions, so I know it's tempting, but you realize that the second term here, x minus 2 over x plus 3, is always going to be negative because the numerator is less than or equal to 0 while the denominator is greater than 0. So you can't just put it into AMGM, you're going to get a bogus conclusion. Now, instead, we're going to use something a lot simpler. Right? But I'm first going to do a little bit of a simplification to what's on the inside. So 2x plus 4 plus x minus 2 over x plus 3. I want to understand this a bit better, so I'm going to rewrite it as 1 minus 5 over x plus 3. The 5 comes from x plus 3 minus x minus 2. Now the reason why I do this is because once you reach here, you notice that you have a rather clear dynamic of how this function behaves. Now this is increasing in x. 5 over x plus 3 is decreasing. But you're taking something increasing minus something decreasing. So which means that the overall function, at least what's inside the bracket, this is increasing. Now you know that in order to find the maximum value of the square of it, you should just then check for the extreme values. So the square is maximized either, okay, let me write this properly. So the square is maximized when the absolute value is maximized, which means it can either be very positive or very negative. And so all you need to do is to check 2 and minus 2. So you check the endpoints. Now there are some allusions to calculus here. I'm not using any calculus at all, but if you are familiar with calculus, you could have differentiated this. Anyway, checking the endpoints, 2 and minus 2, it would give you that f of 2 is equal to 8 squared, which is 64. For f of minus 2, the 2x plus 4 disappears, but what's left is just minus 4 squared, which is 16. So therefore, the largest possible is 64. Next up, question 14. Given that d equals to, and this is a really annoying glut of square roots, the square root of x squared plus y minus 1 squared plus the square root of x minus 1 squared plus y squared. And then they said find the minimum value of d to the power of 8. Someone clearly had a rather strange sense of humor here because the extra square root does nothing when you're looking at d to the power of 8. So all you need to do is to get the minimum value of this x squared plus y minus 1 squared plus x minus 1 squared plus y squared. Now intuitively, what you want therefore is that you want your x, y as well as x minus 1 and y minus 1 all to be fairly small. So if you try x equals to half and y equals to half, that actually would give you an equality case. So intuition would get you to the right answer here pretty quickly. But let's try to do this properly anyway, assuming that we did not want to use intuition in that way and we wanted to know for sure why that's the minimum. Now I will just claim that it's pretty clear both x and y should be between 0 and 1. And the reason is that if you exceeded that range, by shifting it back to 1 or 0, you would have made both of the squares smaller. So if you make them both smaller, then the overall is obviously smaller. So this is the only range that you want. Because of that, I'm going to do something here which will only make sense if you have seen these kind of questions before. What I'm going to do is that I'm going to change this expression into 1 minus y squared, because y minus 1 is not a positive thing. 1 minus y is actually positive. And similarly, 1 minus x squared plus y squared. Now why do we do this? Well, this kind of reminds us a bit of something which we have seen, which is either Pythagoras theorem or the distance formula, depending on which of them is more familiar to you at this point. So this actually can be thought of as a pair of distances. We start off at 0, 0, and then we go to x, 1 minus y. And then we increase the x coordinate by 1 minus x, and we increase the y coordinate by y, so you get 1, 1. And basically what we have over here is the sum of this length plus this length. So how do we make this as small as possible? The minimum would be when x and 1 minus y, this point, is on the line. By the triangle inequality, you hope that it is on the dotted line. In other words, it should be when x equals to 1 minus y, so that it is on this straight line. But in any case, wherever you put it on this line, the total distance is just the distance between 0, 0 and 1, 1. And so the total distance is always square root 2. Okay, so then we just have the mild nuisance of getting the answer at the end. So d is actually the square root of 2. And so d squared is square root 2. D to the power of 4 is 2. And then d to the power of 8 is 4. I think this showed up in the SMO Junior sometime recently, a couple of years ago. At that time, it was kind of packaged under completing the square because they didn't write it in terms of x and y. There was only one variable x. Next up, question 15. Find the minimum value of 8 over sine 2 theta plus 12 tangent theta, where theta is in the first quadrant. Well, this is probably not the typical two things to see together. Sine 2 theta and tangent theta seem a little far apart. Now, if some of you are familiar with the tangent half angle formulas, you could use this and try to rewrite it in terms of something with sine 2 theta and cosine 2 theta. But I'm going to go down a more traditional route because the tangent half angle formulas may not be common knowledge, but the sine double angle formula is certainly common knowledge. So let's go with the one that is more well known. So I'm going to write everything in terms of sine and cosine, which is often a good enough idea if you are not sure what to do. So sine 2 theta is 2 sine theta cos theta. 12 tangent theta is just 12 sine theta over cos theta. Going to simplify a bit and combine it into a single fraction. So the first one is just 4, and the second one is 12 sine squared theta. Now, I said something earlier on, if you remember. I said that whenever you see any quadratic expressions for trigo, like sine squared or sine times cosine, I will try to push it to a double angle. But here I take that back a bit, because if you push it back to a double angle, you're just getting the original sine 2 theta. So let's not push it back to the original thing. Instead, I'm going to look at this sine theta cos theta and sine squared theta, and almost in a meta sense, you can say, they've already asked me to complete the square, and they've already asked me to do look at the increasing function. They've already asked me to use the R formula. So I think if I want to do a minimum value here, it might not be one of those again. And instead, what you can use here is AMGM. But not in its immediate form, because 4 plus 12 sine squared theta is not going to give you anything nice in AMGM. Because when you have AMGM, you hope that the geometric mean at the top would give you sine theta times cos theta, which is not there yet, because there's no cos theta to be found. So I'm going to rewrite 4 as 4 sine squared theta plus 4 cos squared theta. Now, of course, I can group together the 4 and the 12. So now you have got 4 cosine squared theta plus 16 sine squared theta, all divided by sine theta cos theta. At this point, what we have in the numerator, we can use AMGM for that. Now, by AMGM, this is greater than or equals to 2 times of the geometric mean, which is just 16 cos theta sine theta. Therefore, you divide off, it tells you that the minimum value is 16. Now, let me also mention that the equality case should be checked. However, in this case, if you want the two of them to be equal, it just means that sine theta is half of cosine theta. In other words, tangent theta is half. So definitely the equality case exists at tangent inverse of half. But we don't need to really work that out in too much detail. Okay, next one, question 16. This one is, accident. This one's a little bit annoying because it does require quite a lot of familiarity with trigo identities, both familiar and less familiar. But let's see how this goes, shall we? So determine the largest angle theta in degrees from 0 to 360 such that, well, sine of these 4 different angles summed up equals to 1 plus the cosine of these 2 different angles summed up. I don't think this is one of those questions where you can possibly guess theta given an arbitrarily large amount of time unless you knew what to do over here. The first thing is whenever you see any very oddly specific constants, you should ask yourself anything interesting about these oddly specific constants. Now you realize that these two sum to 180, these two sum to 360, and then these two sum to 540. So whenever there are any very strangely coincidental properties of the angles that they give you, it's probably not a coincidence at all. So I would try to shift these into a so-called nicer place by using my symmetry properties of the unit circle. So the first thing I would do is to move all of the angles at the back into something resembling the first quadrant. Now there are multiple ways to do this, but I'm just going to do this in one way. So the first one, no need to touch it. For the second one, I'm going to use sine 180 minus x equals to sine x. So that would shift it over to 180 minus this, which is sine of 18 degrees minus theta. For the third one, I'm going to use sine of sine of x minus 180 degrees is negative sine x, which is just the reverse of the one on top. So you just subtract 180 degrees this time. And if I subtract 180 degrees this time, you get minus sine of theta plus 54 degrees. And finally, for the last one, I'm going to take 360 degrees minus x. And this is negative sine x. So these are all the symmetry properties on your unit circle. However, if you memorize them, that's good. Personally, I prefer to just think of it as reflecting around the unit circle rather than to remember all of these. So this would become minus sine of 54 degrees minus theta. Meanwhile, on the right side, cosine theta plus 60 degrees, I will leave it. And the theta plus 300 degrees, I'm just going to shift it backwards by 360 degrees. All of this is a lot of work, but remember the intention is that you want to shift it all into the first quadrant, and once these two angles basically have the same basic angle, by shifting them back to the first quadrant, you know that it's going to be the same angle, and now your sum to product identities are in play. So let's use the sum to product 3 times on this. I don't think I need to specify which pairs we're going to use the sum to product on. The first pair, sine theta plus 18 sine 18 minus theta, would be 2 sine 18 degrees cos theta. The next one is you subtract off 2 sine 54 degrees sine theta. Cosine theta, beg your pardon. Meanwhile, on the right hand side, you get 1 plus 2 cosine theta cosine 60 degrees. And so you realize, oh, okay, at least the 60 degrees is not going to cause me any trouble at all, since cosine 60 degrees is half, and then 2 times of that is just 1, so that's gone. So I move it over to the other side, and we have a little bit more annoyance, because this is 2 sine 18 degrees minus 2 sine 54 degrees minus 1 cos theta equals to 1. Yeah, so the annoyance here comes in the fact that at the end of all of our work, we still need to figure out how to solve sine 18 degrees minus sine 54 degrees. Because that's really what's stopping us from finding theta. So we need sine 18 minus sine 54 degrees. If you actually search this out, there are quite a lot of discussions on how you can evaluate this because this is a very, I can't say very famous, right? But it's a very interesting identity that this gives you something nice. And I'm just going to show one elementary way of evaluating this. There are a few ways that you can do this, but I'll show one. Now the way that I'm going to show is I will switch it both to cosines first. So I need cosine 72 degrees minus cosine 36 degrees. Right? This is the same thing. Now I will use the double angle formula to form one equation. Cosine 72 degrees equals to 2 cosine squared 36 degrees minus 1. And I will form another equation as follows. Cosine 36 degrees is actually negative of cosine 144 degrees, which is by flipping it over the y-axis on your unit circle. And then I use the double angle identity on this one to get negative 2 cosine squared 72 degrees minus 1. If you add these two equations up, cos 36 degrees plus cos 72 degrees is equal to 2 cosine squared 36 minus 2 cosine squared 72 degrees, which can itself be factorized into 2 times the sum and the difference. I am clearly running out of space. But essentially, this tells me that since cosine 36 plus cosine 72 is obviously not going to be 0, I can divide it off, and cosine 36 minus cosine 72 degrees is half. Is minus half. Cosine 36 degrees minus cosine 72 degrees is half, so cosine 72 minus cosine 36 is minus half. I beg your pardon, it looked a bit wrong when I realized sine 18 is smaller than sine 54. So this is minus 1 half. If some of you are eagerly waiting to type into the chat, how would anyone think of this? I agree. This is a question that will reward prior knowledge of this identity. Here I'm just presenting why it is true. I don't think that it is very easy to come up with this on the spot, since there doesn't seem to be anything straightforward about working with these. I think there are alternatives. You can use the triple angle identity, or you can even use things like complex numbers, or you can use Vieta's formulas. There are a lot of exotic ways to deal with trigo. But in terms of SMO senior level stuff, not easy to think of this. But anyway, once we have got this boxed up info, substitute it back. That means that 2 sine 18 minus 2 sine 54 is also negative 1. So minus 2 cosine theta equals to 1. Cosine theta is minus half. And cosine theta equals to minus half. Cosine is negative in the second and third quadrant. The largest value of this would be 240 degrees. Yeah, admittedly quite a slog, right? How would you actually think about sine 18 minus sine 54 equals to minus half? That's the main challenge. But the ones at the front are just unit circle identities and sum to product, which are still relatively standard results for trigo. Okay, and we hit another geometry question. Question 17. Let O be the circumcenter of the triangle ABC, and ABC is 30 degrees. If you've done any geometry, you know that your sensor should tingle the moment you see 30 degrees. You should be really suspicious. What does that do here? Okay. Let D be a point on the side BC such that the length of AD is the same as the radius of the circle. Okay. This is equal. Determine the value of angle ADO in degree. I really think this is a bit odd that for this whole paper they keep using degree in the singular. Find the value in degrees if angle OAB is 10 degrees. The 10 degrees is more or less there for info, but the 30 degrees is the star. You can do a whole lot with the 30 degrees. Remember that you're inside a circle. So when you're inside a circle, there are lots of things you can do, but one of those things is whenever you see a 30 degrees, you know that the angle at the center will be twice of this. So the angle at the center will be 60 degrees. And if the angle at the center is 60 degrees, that means that we have ourselves an equilateral triangle. So ACO is equilateral. And if it's equilateral, then we have two more equal lengths. So AC and OC is also equal to AD and AO. In particular, this means that AC and AD and AO are all equal. So we can do something nice here, which will speed things up. We can say that A is also the circumcenter of CDO. And I'm just going to draw another circle here. The purpose of this is to expedite whatever we do in finding those angles. So essentially, if you draw another circle, whoops, okay, I am really unable to draw a nice circle centered at A that passes through those points. Let me try my best. This is a bit odd, sorry for the... This is hopefully not going to keep on recurring. Okay, seems fine for now. Now when you have this, it means that you can also use some circle properties in this green circle. Because you want to find angle ADO, and triangle ADO itself is isosceles, so it suffices to find angle DAO. So let's do this. Angle DAO in my green circle is 2 times of angle DCO. And angle DCO is actually the same as angle BCO. I'm just going to change the focus because now at angle BCO I want to focus on the original circle. Since BCO is also an isosceles triangle, there are lots of isosceles triangles in the circle, don't forget that. So 2 times of angle BCO is just 180 degrees minus angle COB. And angle COB in the original circle is 2 times of angle CAB. Angle CAB is 60 degrees plus 10 degrees. So 180 minus 140 is 40. And 40 degrees is angle DAO. Angle ADO is just 180 minus 40 over 2. Because triangle ADO is also isosceles. Okay, you did not need to draw the extra circle over there, but you would needed to have found those isosceles triangles and the 60-degree angle and used all of them. So by drawing the extra circle there, it just allowed me to invoke the circle property instead of doing angle chasing more manually. Okay, question 18. Take a look at the remaining problems. Okay, I think we'll do question 18 and then we'll take another short break. So question 18, function f satisfies fx plus 1 equals to x squared plus 3x for all real numbers x. If f1 plus f2 equals to 25 over 6 and f1 is between 0 and 2, determine the value of 11 times f of 10. Well, I think what everyone would do at the start is to say, they gave me something about f1 and f2, they gave me some more about f1, and then I can substitute x equals to 1. Why not? So let's do that first. So f1, f2 equals to 4. Right? That's the substitution. And at the same time, f1 plus f2 is 25 over 6. So if the product is 4 and the sum is 25 over 6, we certainly can solve this in a whole variety of ways. You could do a substitution and solve the quadratic. I'm just going to fast forward this a bit and say, you know what, f1 is 3 over 2 and f2 is 8 over 3 would be the result of any way of solving this. Now take note that the condition here, 0 and 2, tells you that you should have 3 over 2 as f1 instead of 8 over 3 being f1, because just based on the two equations alone, the values could have swapped around. But the condition tells you that the 3 over 2 should be f of 1, 8 over 3 should be f of 2. Okay, the next thing they ask you to find is 11 times f of 10. Now you notice that based on these equations, this functional equation, you could have substituted x equals to 2 and then use that to find f3. Then you substitute 3 to find f of 4. So if you are in the SMO and you have solved a bunch of other questions and you have no idea what else to do, that would certainly have been possible if you wanted to solve one more question and were willing to deal with a lot of fractions for the next 15 minutes. However, let's look at how we can avoid writing down that super long list of fractions one by one. Now if fx plus 1, equals to xx plus 3, I'm going to write it as a factorization so that it's easier later. If I replace x by x plus 1, that means the next number. The next number, fx plus 1, and then fx plus 2. This would be x plus 1, x plus 4, because everything now has increased by 1 when I replace x by the next number. If I divide this 2, it gives me the ratio fx plus 2 over fx is equal to x plus 1, x plus 4 over x times x plus 3. Now this means that I know the ratio, I can jump forward by 2 steps every time, And in fact, I know that I'm just going to multiply by the ratio from 2 to get 4, from 4 I get 6, from 6 I get 8, from 8 I get 10. So I can combine all of this together and say f of 10 equals to f of 2 first. Sorry, erase this and write that properly. You start with f of 2, and then you multiply by the ratio, and then you multiply by the next ratio, and you do that 2 more times. So I feel like writing dot dot dot, but there's only 2 more, so I should probably just write them both out. Now each of this is just going to give you some numbers, and why I left it in factorized form is that those are going to cancel out. So most of those factors will cancel out if you leave it in factorized form, versus if you wrote it as x squared plus 5x plus 4, then you will end up calculating a lot of numbers and doing a lot more multiplication than we would like. So the first one's 8 over 3. For f of 4, you substitute in 2. So 3 times 6 over 2 times 5. The next one, everything increases by 2. So you substitute in 4, 5 times 8 over 4 times 7, followed by 7 times 10 over 6 times 9, and finally 9 times 12 over 8 times 11. Now a huge bunch of these are going to cancel out, specifically 5, 6, 7, 8, and 9 are going to cancel off. You can also cancel off 3 here, and 8 is 2 times 4. So we are left with only the 3 numbers at the back, 10, 12, and 11. This is 120 over 11, and so your answer is 120. Alright, so I think we will take another 5-minute break here, and then once you're back, we will deal with the last 7 questions. Okay, welcome back. So we're going to wrap up the last 7 questions, and then you all can have a good rest, especially if you took the SMO open this morning. Question 19. Find the value of this big chunk of 1 over sine squared minus tangent squared, 1 over sine squared minus tangent squared, and so on. And it goes from all the half degree, so half a degree, 1.5, 2.5, until 179.5. The first thing I would do is, I would ask myself, wait a second, is there some identity for this? And if you rewrote this 1 over sine squared as cosecant squared, you realize that, we are close, but no cigar. Because cosecant squared minus tangent squared is not the identity. The identity was actually cosecant squared minus cotangent squared, or secant squared minus tangent squared. So we are not quite there, unfortunately. But it does give you some idea that you wouldn't mind if you could get that sort of cancellation to occur, such that there's a bunch of 1s everywhere. Now, I may forget a degree sign once in a while, just pardon me for that. Now, one thing that I would do here is that I can actually fold this inwards, because everything is cosecant squared and tangent squared. Now, you know that when you take something and do 180 degrees minus that angle, for sine, cosine, tangent, secant, cosecant, cotangent, regardless, you're going to either keep them the same or negate it. But if you square it, it will always stay the same, because if it was positive or negative, the square will end up the same. So any trigo thing, squared of theta, would always be the same as that same thing applied to 180 degrees minus theta, where the box can be anything, sine, cos, or it can be tangent, or even cosecant, cotangent, secant, because those are reciprocals. So everything from 90.5 to 179.5 can be folded backwards into 89.5 back to 0.5. So I'm going to just do that for convenience sake. And I can stop at 89.5 this time. So you want to make use of this kind of symmetry arguments. Now the next thing that I'm going to do is that you realize that cosecant is 1 over sine squared. So since cosine theta is sine of 90 degrees minus theta, cosecant of theta is also secant of 90 degrees minus theta. In fact, that's why it is called that, because cosecant of theta is secant of the complementary angle. Right? So that's the same relationship, sine and cosine, secant and cosecant, tangent and cotangent. It means that it is the same thing but for the complementary angle. So I'm going to switch it now from cosecant to secant, but with the angles being flipped over as well. So this would now become secant squared 89.5 and then this would become secant squared 0.5. So the order of them has reversed when I change it from cosecant to secant. But then you realize, hey, they're all still there, right? Even though I reversed the order. So you can actually group together all of these as secant squared minus tangent squared. They're all somewhere in there. And we know that secant squared minus tangent squared is 1. Now I know that some of us may be used to sine squared plus cosine squared equals to 1, but for some reason we do not use tangent squared plus 1 is secant squared. Now that's really useful because of a couple of reasons. One, it allows us to avoid switching every single thing to sine and cosine. And second of all, as you would see when you do some calculus, we cannot avoid using tangent and secant once in a while. Cosecant and cotangent may be still okay, but secant and tangent, you will still need them. Anyway, there are a bunch of stuff that are all equal to 1, so it is 2 times 90, and the total is 180. Next up, question 20. Now, when I first saw this question, I scrutinized very carefully, is this thing symmetric or is this not symmetric? And actually, it's quite hard to tell whether it is perfectly symmetric or not because all the signs of A1 minus A2, A2 minus A3 can potentially be confusing. So let me number these equations 1, 2, 3 first. A1, A2 and A3 are 3 distinct integers, descending order somewhere between 1000 and 0, and x, y, z are just some real numbers such that these are true. So this doesn't seem to have any nice reason. There may be something to do with differences here, but we're not quite clear what is the big deal about it. However, on the right side, A1 plus A2 plus A3 appears 3 times. Over and over again, this turns out to be the same. And so it suggests that if I don't know what to do, let's subtract the equations because the right side is going to be 0. Maybe you'll tell me something. So let's try subtracting the equations and see what we get. Firstly, take the first minus the second. Now the first minus second, you get A1 minus A2y minus A1 minus A2x. And then A1 minus A3, you subtract A2 minus A3, it is also A1 minus A2z. Hey, that can be factorized as A1 minus A2, y minus x plus z equals to 0. Now since the A1, A2, A3 are distinct integers, that can't be the 0, so therefore this must be 0, and let's write it down at the top. So y minus x plus z equals to 0. Hey, I haven't used the other equations as well, especially the third one. I can combine either the first and third or the second and third. So let's see how that turns out. Now, there are probably 2 other things you could do. Either you do 1 minus 3 first or 2 minus 3. I'm just going to do 1 minus 3. Now in this case, you get A1 minus A3 for both z and x. Right? A1 minus A3z minus A1 minus A3x. But for the y's, they don't cancel out that nicely. They actually give you A1 minus 2A2 plus A3y. So we can't quite do that much with it yet. Unless you realize that, hey, z plus y minus x is 0, means that I can take out all the A1 minus A3s with this z plus y minus x. So there's a z, there's a minus x, and let's take a y as well because I want that to be 0. Now, having taken out A1 minus A3y, it follows that I'm left with 2A3 minus 2A2y equals to 0. Well, what do I know? I know that this is 0 over here. So the left side is 0, the whole thing is 0, so the right side is 0, but A3 minus A2 also can't be 0. So therefore y must be 0. And that's a much better conclusion than you would expect. Y must be 0. And so the first equation tells you that x is equal to z. Now let's substitute it back into the equations then. Now that we know y is 0 and x equals to z. No matter which equation you substitute into, your conclusion is going to be the same. Namely, a1 minus a3 x equals to a1 plus a2 plus a3. And you can divide over. X becomes the sum of the three numbers divided by the difference between the first and the last one. Now, oh no, this is not enough information for us to find x. So what do we do? Well, you read the question again, and it tells you that you don't want to solve it, you only want the largest possible value. So since you only want the largest possible value, you want the sum to be big but the difference to be small. So what better than to just make them 999, 998, and 997. Right? You make the difference as small as possible and the sum as big as possible. Obviously, the quotient will also be as big as possible. Now you would conclude then, after writing this, that x equals to z equals to 1497. That's after calculating it. And x plus y plus z would be 2 times of this, which is 2994. Maybe there's some more clever way of combining this and adding and subtracting, which I'm sure that based on these choices, maybe you take 1 minus 2 plus 3 or 1 plus 3 minus 2 or something like that, and it will work out even better than what I've done. I'm sure there must be something like that. But I think this is the most intuitively logical approach. You just try to make them cancel out by subtracting equations, since the right hand sides are all the same. Okay, 21. The figure below shows a circle centered at O with radius 555 cm. If OA equals to OB, and RA over AS plus RB over BT equals to 13 over 6, find OA in centimeters. To be honest, if I were doing the SMO, there's a very cheap way to solve the question. And the cheap way is to assume, what is it called? A cheap method. The cheap method would be to assume that R is at P. Now, how would that actually look like if you imagine that you push R all the way onto the diameter? Don't worry, I'm going to show you the proper method later. This is just something that I realized would actually give you the correct answer, since there was no information about where your point R is. Right? R is just an arbitrary point that satisfies this equation. So imagine that you put P and R at the same place. O is here, A and B are somewhere here. Now if you put R there, then S and T would both end up the same place at Q, because you extend R through A and you hit Q. You extend R through B and you hit T. So Q, S and T would all be at the other side of the diameter. So this becomes a really silly question then if we do that, because it means that you have got two lengths here. We call this X and 555 minus X. And you can just substitute in and solve. If you solve, it will give you your answer. X is 111. Now I mentioned this because there are lots of questions where you can perform this kind of tricks, and if we constrain ourselves to thinking that the only trick for this kind of question is to draw it accurately, you're not going to know how to draw this accurately if you have to make it 13 over 6 exactly. Where do I put my point R? Okay, so this is the unintended way of solving it. What's the intended way of solving it? Well, OA equals to OB. I want to make use of this in some way. The easiest conclusion is that QA is also equals to PB, because that's the rest of the radius. Now I'm going to call the length I want x still. And I'm not going to use 555, I'm just going to use r, because I don't want to do multiplications with 555 too many times. So I'm going to call this just r minus x. Okay, so r is 555, but I don't want to put that all over the place in my working. Now the first thing I'm going to use is the fact that a and b are equidistant from O means that if you use power of a point, or again your intersecting chords theorem, that means that if I focus on point A, RA times AS, which mind you are the two things in your fraction, is equals to QA times AP. And QA times AP is just r minus x times r plus x, which is r squared minus x squared. And you can actually do the same thing for B, because B, if you calculate QB times BP, that will have the same power of a point. QB times BP is also r plus x times r minus x. So therefore this is also equal to RB times BT. So that's the first observation that we can make. Now I'm going to multiply this throughout the equation. So for the first one, I'm going to multiply it by RA times AS. To give me RA squared. For the second summand, the second fraction, I'm going to multiply it by RB times BT, so that I cancel off BT and I get RB squared. And for the third summand, I'm going to just use r squared minus x squared. Now they're all the same, right? So I'm actually multiplying throughout by the same value, but I picked three different representatives of the same value so that this will simplify. And this will be equal to 13 over 6 r squared minus x squared. Okay, so I picked three different things to multiply it. That's one equation. Now I'm going to get a second equation, and that second equation can come from a variety of ways. I'm going to join RO which is also going to have length the second equation. However, I'm going to reference a question from last year's SMO, an identity, which is that in any parallelogram, this was in last year's question, right? You can have the two sides. The sum of squares of the sides is half times the sum of squares of the diagonals. So this was the specific question at that time with some values, but I'm just going to use the identity. And the reason why I want to use the identity is because it will relate back to RA squared plus RB squared again. But you might ask, wait, that doesn't make sense. Where's the parallelogram? And the answer is you can extend it the other way, to the other side. Let's call this point PQRST, let's call it V. Now, RV is a diameter, so it means that this is a parallelogram. Since you're just drawing from one side to the other side, and the diagonals bisect one another. So since RAVB is a parallelogram, we have a second equation, which is that RA squared plus RB squared equals to 1/2 of the sum of squares of the diagonals, which is 2x squared plus 2r squared. And this is, of course, equals to 2x squared plus 2r squared. So now we take this equation here along with this equation here, and it gives you the relationship between r and x. Okay, we solve this. 1/6r squared equals to 25 over 6x squared, which means that r equals to 5x. You see why I didn't include 5, 5, 5 everywhere? Because actually everything can be just written in terms of r first, and then you only substitute at the very end. And therefore x is equal to 111. You might have tried to do this question using similar triangles. The problem is that RA over AS does not ever give you something in your similar triangles. In your similar triangles, you would get RA over AQ. And that's the reason why we needed to use something else to give us a useful equation. Now, depending on how comfortable you are with number theory and combi, the last few questions can either be very easy or very difficult. Question 22 is one more that is algebraic, but actually towards the end, you see, it is not actually getting harder, it's just changing focus. Okay, so let's look at this. Question 22. Find the number of real solutions xy of the system of equations x cubed plus y cubed plus y squared equals to 0, x squared plus x squared y plus xy squared equals to 0. Hey, so that actually seems to be quite nice because both right hand sides are already 0. And one obvious thing is that there's actually a factor of x in the second equation. Yeah, okay, for the previous question, what happens if we don't see the parallelogram? In that same triangle RAB, you could have used either the cosine rule, or you could have used Stewart's theorem or Apollonius theorem. So if any of those names sounds familiar, you can use that to give you the same equation at the end. And you don't need all of them, you need any one of them. Okay, so anyway, back to here. X times x plus xy plus y squared equals to 0 means that I shall split quickly into two cases. The first case is x equals to 0, and I shall leave very little space for that because, as you can tell, that isn't a very difficult case to deal with. If x is 0, the second equation is already done. Y cubed plus y squared equals to 0, which you can factorize into y squared y plus 1. So y is 0 or minus 1. So that's two solutions, right? 0, 0 or 0 minus 1. Now what happens if we have got x plus xy plus y squared equals 0 and x cubed plus y cubed plus y squared equals to 0? Actually, we have quite a lot of choices of next steps from here. But it's really up to you. You want to make some things cancel out, right? And you realize that if you want to make some things cancel out, you don't want just one term to cancel out. You hope that two terms can cancel out. In order for them to cancel out, you need the terms to be in the same ratio, meaning that you can multiply by a constant such that both of them are the same. And so I'm going to look at this because x and xy is just a factor of y apart. Y cubed and y squared are just a factor of y apart as well. So I'm going to make these two pairs become the same. So I multiply the first one by y squared. And then you get xy squared plus xy cubed plus y to the 4 equals to 0. For the second, the other equation, I'm going to multiply it by x. So x to the 4 plus xy cubed plus xy squared equals to 0. And take note again that what we have just done is to try to make the highlighted pair of terms the same, which indeed is what you get. Right? You match x with y squared and xy with y cubed. So subtracting these two, you get something nice. You subtract. It tells you that y to the 4 minus x to the 4 equals to 0. Okay, this one can be pretty easily factorized into a difference of squares, which you can factorize further using difference of squares again. And the sum of squares cannot be 0, since that case is already covered for x equals to 0. So that means that the only possibilities are x equals to y or x equals to minus y. Now if x equals to y though, and you substitute in, you will see that you get a really simple pair of equations. If x equals to y, both of them become 2x cubed plus x squared equals to 0. And so since we don't want the x equals to 0 solution, you can actually solve and find that x equals to minus half is the other solution. Now, however, if x equals to minus y, then it would just reduce to y squared equals to 0. And that would give you y equals to 0, which we don't want since we have already counted that here. So let me just write that already counted. So the only new one that we found through everything we wrote on the right side is x equals to y equals to minus half. So there's one more solution, and altogether that gives you 3 solutions to this equation. Good, we're almost there. So finally we get to some things that are not algebra and geometry. And question 23 is a combinatorics problem. You have a 3 by 5 rectangle consisting of, well, 15 small squares. How many ways are there to color 9 out of the 15 such that every row and column has an odd number of black squares? When you're doing combi, you want to start with something that is as restrictive as possible. Meaning that you don't want to start with, okay, I can either paint this one black or don't paint it black. Then I can either paint this one black or don't paint it black. Don't start with that, because there are so many ways that something can be or cannot be black. Look at the condition for every column has an odd number. It means that every column is 1 or 3. This is not 1/3, this is 1 or 3. And they have to sum up to 9 black colored squares. So that means that you need 2 columns with 3 and 3 columns with 1. That's how you get 9. So 2 columns with 3 and 3 columns with 1. To find out how many black squares we can get, this is not too bad, because we can just choose 2 of the columns to have 3, and any 2 columns can be 3, this should still work. So the number of ways to do this is just 5 choose 2. So 10 ways to decide. Let's say now you have assigned the one of these 10 ways, right? And we'll just use a specific example to see. So for each of these 10 ways, let's say that the first and the last column have 3 and then these middle ones have 1. Now that means that since you have assigned them to have 3, you have no more choices left, right? This must all be black. Now what do you do with the remaining 3 rows? 3 columns. Because every row has to have an odd number of black squares, and currently you have just filled up 2 each. So you need 1 more here, 1 more here, and 1 more here. Which means that you need to, in the remaining 3 by 3 square, you need to just put in 1 in every row and column. So that means that for the first one, you have 3 choices. So to place black squares. For the first column, you have 3 choices. Now let's say you put it here. For the next column, you only have 2 choices. And for the last column, you only have 1 choice. So that's just 3 factorial. So there are 10 ways to assign it, and 3 factorial ways to place the squares for those columns with 1 black square to put. So just multiply. 10 times 3 factorial equals to 60. So in this case, we started with the global condition, which is pretty restrictive. The columns can only have 1 or 3. So once you know that's the case, you can decide how many should have 1, how many should have 3, assign them first, and then once you have assigned that broad configuration, you just decide which ones exactly to put the black squares into. Okay, 24. Let n be a positive integer such that 2021n over 2021 plus n is also a positive integer. Determine the smallest possible value of n. It is used to be quite a staple in the SMO, sometimes junior, sometimes senior, sometimes open. And if you have seen it before, you should know exactly what to do. Now, if not, here's the idea. If you have 2021n over 2021 plus n, what we can do is we can do a bit of long division. And the reason why we want to do long division is I want to get the numerator to become just the remainder. So if I put 2021 as my quotient, I get 2021n plus 2021 squared, and so the remainder is negative 2021 squared. So that means that this can be written in the following way. It is 2021 minus 2021 squared over 2021 plus n. Now you're supposed to find the smallest possible value of n such that the whole expression is a positive integer. So that means that this must be a positive integer. And if this has to be a positive integer, then it means that 2021 plus n must be a factor of 2021 squared. I've seen that the SMO Junior yesterday went wild with this, and basically 2021's factorization has been pretty important to know this year. 43 squared times 47 squared, since there is a square this time. Remember, you need the factor to be more than 2021, which is 43 times 47. So the next biggest factor after 2021, it's quite clearly 47 squared, because that's bigger than 43 times 47. So you should let 2021 plus n be 47 squared. So we subtract it off, then n would be equals to 188. Okay, and finally we are at question 25. So it looks like we're going to finish at 6 o'clock as we had hoped. Determine the number of 5-digit numbers with the following properties. All the digits are non-zero, the digits can be repeated, and the difference between consecutive digits is exactly 1. Now what's the big problem here? Now the big problem comes with the fact that sometimes you have more choices than others. So let's say, for example, if you started off saying that the first digit is 1, then the next digit must be 2 because they are consecutive. Then the next one can either be 3 or 1. Now if it's 1, then 1 can go to 2, but if it's 3, then 3 can go to 2 and 4. And so you realize that, oh no, this is actually going to be quite messy, because at various points in time, you may break off into more possibilities. So here's how we can avoid breaking off into many possibilities. Instead of starting at the left, let's start in the middle. Now why do I want to start in the middle? Because from the middle, you only can take 2 steps to the left and 2 steps to the right. So you don't have to worry so much. Now let's say that all the digits must be between 1 and 9, right? Since 0 is not allowed. If let's say that in the middle is 3 to 7, you will never ever run out of space. That means that you will never hit the boundaries of hitting 1 and 9, except for right at the very end. So from 3 to 7, you know that you're going to have 2 choices here, whatever your choice, and 2 more choices here after that. So for example, if it's 3, then you could go to 2 or 4. From 2 is 1 or 3, from 4 is 3 or 5. So you're always going to get 2 times 2 choices. We do the same thing here. On the left side, it will be the same as the right side. So this would be 5 times 2 to the power of 4, which is equal to 80. Now if let's say this is 2 or 8, in both of those cases, let's say you have 8, you can either go down, down, you can go down, up, or you can go up, down, but you cannot go up twice. So you basically lost one possibility. You cannot go from 8, 9, 10. You cannot go 2, 1, 0. So that's the only one that you're not allowed to. Other than that, the other 3 cases are fine. So 4 minus 1 is 3, which is on both the left and right. So 2 choices in the middle, 3 on the left and right is 18. Now finally, if it is 1 or 9, then the one on the left and right are just fixed. So if you start at 1, you can only go to 2. If you start at 9, you can only go to 8. So there's only one choice here. But once you make that choice, the one at the extreme end, you have 2 choices. So this is 2 times 2 squared equals to 8. So summing up, 80 plus 18 plus 8, you get 106 such numbers. Okay, do I plan to go over past year SMO papers? Possibly. So I do want to do other stuff apart from the SMO, possibly the AMC or some other competitions that are relevant, maybe go upwards to, let's say, AIME or IMO shortlist level, maybe go downwards to some primary school competitions as well. So I haven't quite decided yet, but for now this is SMO season, so we're going to stick to the SMO at least for this couple of days and see how again later. Alright, so we're actually at the end of the paper. Any questions or clarifications on whatever we have gone over? So in the meantime, as I'm waiting for that slight latency in the stream to see your responses, I want to say thank you for joining this stream today. If you have enjoyed it, again, without self-promotion, please like the channel and subscribe. And like the video and subscribe to the channel. Still new at this. And if you have any alternative suggestions you think of later, you can always write it in the chat. If you say that, I actually think there's a better way to do this question, you can write it down, and hey, anyone else that ever sees this video would see that you were the person that came out with this better solution. So you get a little bit of internet fame as well. Now, I will be doing the SMO Open review tomorrow as well. So for those of you who are in Sec 4 especially, next year you have to take the SMO Open only. So perhaps if you want to get a glimpse of how it's like, whether or not you took it this morning, you can always join in the session. It will be at 3 PM instead, for the very simple reason that I think the SMO Open might need a bit more time, and looking at the paper, I think I was right. So I may need 3 hours for it tomorrow. I will see how it goes as I plan out the solutions. Now don't be too discouraged if, let's say, the outcome for the SMO was not as good as you expected. For one thing, the questions difficulty seems to be a bit higher compared to previous years. But even then, right, even if you said, no, it's not the difficulty, I just did really badly, don't worry. Right? There will always be other competitions and more chances to take the SMO again. Alright, so if there's no other questions, what I'll do is I will turn off the camera first. I will leave the stream on for a short while more, so if you have any things you want to discuss in the chat or any questions, you can do so for the time being. Okay, so thanks again everyone for joining in, and hopefully see some of you tomorrow.